drawing from Heather Fletcher from 2016, 5 years ago. And Heather was one of my honor students. She drew this nice picture here. I like the water, it's raining, and it's an umbrella inversion like we did in lab. SN2, so you can see how this SN2 reaction down below, the bromine was wedged leaving group, and then the nucleophile came in, it's dashed, now it inverts. So today, oh, and look, the wind blew her umbrella, inverted it, and she dropped her Erlenmeyer flask. Oh no, she's got to put that in glass waste. All right, and today we'll probably finish chapter 6 and start chapter 7. Don't skip questions in lab assignments. I said this in lab, but I want to really reinforce it. So I know it's tempting to skip questions as you're going through a lab assignment because you want to get to the wet chemistry sooner, but don't do that. It winds up, it's like you're going to the movie theater and you're putting on a blindfold and your noise canceling headphones and you got popcorn and you have your mask on, but you're not going to take it off, so you can't even eat your popcorn. So it's not as good as doing it. So it makes learning less, and it takes longer to complete the assignment in the long run because you're going to probably collect poor data or you're not understanding what data you're collecting. And when you get home, you're not going to be able to ask me for help because you're not right there answering the questions. So this is extra true for the extraction lab. So I want all of you, whenever you do extractions in lab, to be drawing out the extraction diagram as you go. And then tablet users, can you do me a favor? Oh, there's just a few of you who don't do this. Can you answer in different colored font than the question? So if my question's in black, can you answer like in red or something? Then when I'm grading it, helps me get through a lot quicker. And most of you now, when you submit assignments done on your tablets, they come as huge files to me and it takes a long time to download. So I'm hoping we could figure out a way to compress those. I tried yesterday 2 free apps on my iPad. One of them said, oh, I compressed a PDF, and it said, oh, now that's one of your 2 for this week. I was like, oh, that's annoying. They're trying to get me to buy it, which I get it. Maybe I should buy it, but I don't want to buy it. I'm trying to find the free version. And then maybe the app you used on your tablet, maybe like OneNote or Notable, I don't know which ones you use. They might have a feature. You can Google search it, like how do I compress PDFs in OneNote or in this. You might find a way easily to compress it. And also maybe even better than that is if you just answer the questions on a separate file, like start up like a Google Doc or something on your tablet and then just answer your questions there if that's easy. And then it's like just got the questions. It doesn't have all my texts and things. You could probably still, I don't know, unless that's a hassle, try to do it if you can. And then the crystallization lab extra credit. Some of you did it, I think, but I didn't give you credit for it because in the extra credit, it says submit it as a separate extra credit assignment. And when I was grading it quickly, I might've missed it, or I was just like, oh, I wanna just grade this. And then I don't wanna have to like leave this grading platform to go to the extra credit and come back and forth. So please, if you wanna get extra credit for those questions, 29 to 36, turn those in separate in the extra credit area. Just like I was saying earlier about if you find an error in something, turn that into the extra credit area. So when I'm grading, it helps me out a lot. And so you'll find that in extra credits at the top here, finding errors, submit those here, not through email. And then also crystallization extra credit, there it is down there. So don't just have those answers in the doc, in the actual experiment. Okay, and starting Monday, the 15th coming up, the road Eldon will be closed. That's the one you probably maybe don't even know the name of it, but you drive into it to park by this science building. So here, I'll show you what it is. So here's Rockland Road. So the 80 freeway is over here. So when you come into Rockland Road, like me, you might be coming down Rockland Road and make a left into Eldon. And then you got that curvy lane down to the parking lot here. And here's where I am at now, right now in the S building. So this is going to be closed off for construction, but we can still park in the S lot, I think. Seems like it. You just can't turn left on Eldon. You have to keep going up to this road, this entrance towards the end of and then you can drive down around to get into the S lot. So you can still park in the S lot. It's just going to be a little bit of a detour. It's best to watch lecture videos before you're following lab period. I know that's not possible for everyone, but if it's not possible for you, then at least go through the lecture outlines, like today's outline. We have the Stereochem quiz today in lab. The Tuesday, Thursday students took it yesterday on Tuesday because they don't have a Thursday lab. And then the Wednesday people, it's today for you. Homework E, chapter 6 is posted. Start working on that. because that's stuff for the exam. And homework D, that's due today. It's due tomorrow, but that's Veterans Day. So if you got a paper copy, turn that in today or Tuesday in lab, but sooner the better, next Tuesday. All right, prepare for lab this week. Try to, like in all weeks, try to get extractions done this week. And then we can, so we can get the chromatography going. So read ahead, wet lab parts, past wet lab parts to do, more dry lab to get ready. And you can come do lab work during my office hours, like always these times, except for this Thursday will be Veterans Day. So no lab Thursday. Thank you, veterans. And mechanism quiz, SN2 reaction is in lab this coming Monday and Tuesday. That'll help you get ready for the exam. SN2 will be on the exam. And exam details. So we got the exam next week on Wednesday and Thursday in lab. You'll have 3 hours to complete it just like before. You can come early just like before. And place your cell phones at the front, no notes allowed. Come in quietly. While others might already been started on the exam, so come in quietly. And after most people finish, we can do a little bit of lab work. So details about the exam, I was going through today. This is kind of like my outline. I haven't written the exam yet. So the exam will be cumulative, but focused on the following outcomes: all of chapter 5 and 6 outcomes, and perhaps just a little bit of chapter 7. I think I'm going to have you just do the mechanisms for SN1, E1, and E2. So, but I'll let you know for sure after maybe today's or Monday's lecture. The exam will definitely have a question like number 11, 12 on homework D, chapter 5. And now the reason why I said it's number 11, 12 is because I added recently a new number 1 question to homework 5, a Stereochem containing nomenclature question. So if you downloaded homework 5, like last week, then your question, the question I'm talking about on the newest version is 12. Your version might be 11. So I have the question here too to make sure you know what I'm talking about. I like this one. This one's good. You got to figure out how these molecules are related. Are they enantiomers? Are they diastereomers? Are they totally different? And then molecule A, you're given the rotation and the melting point. So then how does that affect? Can you predict these other two? So, and things have been rotated around on them. So you have to figure out R and S and try to figure it out. Yeah, so if you're confused about the number 12, 11, just go to the latest version. I got it linked here. And nomenclature with Stereochem, I have this as number 1 now on homework 5, but it's also, I put it on homework 6 to make sure people see it before the exam. So it's the same question on homework 6 and 5, but if you downloaded 5 earlier, you don't see it on your downloaded copy, but you'll see it there. And then I'll ask a zigzag to Fisher projection or Fisher projection to zigzag like we've been doing in lecture. Practice those, that'll definitely be on there. A radical halogenation of an alkane reaction that involves Stereochem. We're going to definitely have one of those. And this is maybe one of the most difficult type of questions I ask like all year of O.Chem. I don't know for sure, but it's pretty challenging, right? Most organic chemists first year won't be asked something to this depth. But since I'm telling you it's there and we've spent a lot of time on it, I think you'll do well. My students in past years have done really well on this because they know it's coming and they practice. And I have examples for you. This is like 3 examples in this first one, Google slide animation. And then this one in the lecture I went over example. And also in the chapter 5 outcomes at the end of the slides here, 19 to 21, have some examples of this. So you got lots of examples to practice. So you should be able to ace this question. It'll probably be a big point question and you know it's coming. And then the exam will also have questions like 18A and B from homework chapter 5. So it's 18A and B now. I think it might be 17A and B if you've already downloaded it. So, and it's also from the workshop, but here's what I'm talking about. These kind of questions where you have 2 molecules and I'm trying to trick you into thinking they're enantiomers. Are these enantiomers? No, these are just the exact same molecule and they are exact same molecule and they're not meso. Whereas this one here, let me see if I flip that over. Yeah, these are enantiomers. So be good at those. Don't get tricked. I got 18A and B on the newest chapter 5 homework. Has examples of it, and on the Stereochem workshop you have examples of it. And the Stereochem workshop examples, I worked that out last lecture. I love this question. I'm surprised I didn't have this in homework 5. So I added this to homework 5 today. So if you've downloaded homework 5 already, you haven't seen this one yet. So check it out. I'll put it here actually too. This was the type of question I asked. I did an example of when I was first hired at Sierra College. I came here back in 2003, and I really liked this type of question. So I did it as my lecture demo, and that's helped me get hired here way back when, before I had kids. Well, let me see. So Michaela was born. Well, I had a kid, but Michaela was still in mom's belly. So yeah, I like this one. You draw out the reagent right here and the product. And the key thing is the product is achiral. So once you figure out what this product can be, it has to come from this. It's an SN2 reaction. It's achiral, so you have to figure out what could this be? And then once you figure this out, then you figure out the reagent, and then you draw the electrophile and you define the stereochem of X there. So it's got SN2 and stereochem stuff. And then the exam will definitely have SN2 mechanisms with colors. You're going to have that on the quiz on Monday too to help you get going. And we'll be able to rank nucleophiles and electrophiles, like say, oh, this nucleophile is going to react faster than that one. Electrophiles, like, oh, that electrophile is going to be faster in SN2 than this one. And the leaving groups, what's a good leaving group that reacts fast on a electrophile? And also solvents, what's a good solvent to make the reaction go faster? All these topics I think we'll get to today. And I really like intramolecular reactions. I said this before last exam, and I gave you an intramolecular reaction last exam, right? And here's one I asked last year. This was on the exam last year. So this is an SN2 reaction. Let's see if you can draw it where the sulfur reaches around, kicks off the bromine. It makes a 1, 2, 3, 4, 5, 6 membered ring. See if you can do it. It gets tricky with the stereochem. All right, in the exam, we'll definitely have a spectroscopy problem. We always have that, right? So review your IR values, like, oh, what's that big strong one around 1700? Oh, carbon. Oh, it's got a signal in the proton NMR between 7 and 8. Oh, it looks like a benzene ring, that kind of stuff. And then to end off today, James, our honors student, already finished his second honors project. So here it is. Let's check it out. This will be a good review. Oh, wait, I have questions before I start here. Good morning. Noticed that last week, but oh, yeah, sorry about that, Annalise. Okay, so here we go. Here's James's SN1 reaction. Oh, so this is a reaction from chapter 7. We're gonna hopefully start. We might get to this today, but I'll show you real quick. So he does the theme of what? Can anyone tell what this theme is for this one? Yeah, we got New York here. Live from New York. It's Saturday night. It's a Saturday Night Live. So here we go. SN1 mechanisms. With so many SN1 problems out there, O.Chem students are expected to solve them perfectly. However, our guest is a self-proclaimed O.Chem master. Welcome, Pete Davison. I just said that so I can come on. I have no idea what's going on. Seriously, I don't want this to be you guys. I'm still trying to figure out how to make cyclohexane chair conformations with those Lego sticks. So what is your take on these SN1 O.Chem problems? Overall reaction? What kind of a reactant is this, would you guess? I know we haven't gone over SN1, but it's very similar to SN2. Is this guy the solvent, do you think? Do you think this is the nucleophile or the electrophile? I got one vote for electrophile, not the nucleophile, it's the electrophile. It's electron loving. The carbon with the bromine is the carbon that reacts. It has a partial positive charge, so it loves electrons. And then the bromine is the leaving group. So what kind of electrophile is this? Is this a methyl electrophile, primary, secondary, tertiary? Secondary, good. And then this here, the water, that's going to be our nucleophile and our solvent. It's going to have two jobs. And when it adds to the electrophile, I get this wiggly product. Do you know what the wiggly sign means? Anyone? I think I might have just told a couple of you in person. I don't know if I said it in a lecture. The wiggle means that you have a mixture of both wedged alcohol and dashed. So this is a mixture, a racemic mixture. It's a shorthand instead of having to draw them both. And then we got our leaving group came off and we get hydronium. So what is that squiggly thing? Here it is. So it's these two products, like I said, boom. An equal amount means they're enantiomers, equal amount, racemic mixture, achiral. Cool. Racemic mixture. So isn't 2-bromobutane? Oh, isn't the, I forgot, I need to fix this. Is this guy R or S? Let's see. 2 R or S. What's the electrophile? R. 2R, because ABC, yeah. 2R, 2-bromobutane, a chiral molecule. There we go, I like that. Okay, let's adjust that. Oh, now we got it. So isn't that a chiral molecule? And a racemic mixture of 2 butanols, achiral. So we went from a chiral molecule to an achiral mixture. Is that okay? I thought we had some rules, like if your achiral is a reactant, your products are achiral, right? But when your chiral is a reactant, are your products always chiral? Nope, not always. If you have chiral reactants, you could have chiral products, but you might not. And this is a case where you don't. So the first step of this mechanism is the leaving group just leaves all on its own. Crazy, huh? Makes a carbocation right there. That carbon there is missing a bond to the bromide. So this is our first step of the mechanism, and it's our rate determining step. Can somebody tell me what kind of step this rate determining step is? This is not a bimolecular rate determining step. When you want to determine if a reaction is bimolecular or unimolecular, you look at how many reactants there are. How many reactants does this have? Just the one reactant in this rate determining step. So this is a unimolecular rate determining step. And that's where the 1 comes from. SN1 substitution nucleophilic unimolecular rate determining step. Look, the butane molecule turned it into an achiral molecule. So this carbocation is achiral. It lost the stereocenter. It's no longer chiral. So at this point, chirality was lost. So now our final products can't be chiral. Step 2, a water molecule adds onto the carbocation. This has generated these arrows. I'm not a big fan of these arrows, but we're going to make them better. This was generated by the online version of Marvin Sketch, which isn't the best. So, but when this water molecule adds to that carbocation, it can add from our side of the screen to be wedged or the back side to be dashed. So you get a racemic mixture drawn in shorthand, and there's no more plus charge here. Darn it, sorry. There it is. Get rid of that plus charge. Bye-bye plus charge. Yeah, let's draw a line in here. That looking better? I think that gray works pretty good. Close enough. All right. So yeah, so that's now that water molecule's got the plus charge, and yeah, I'll fix that later. Oh, it's still there, of course. I didn't notice that when I was checking this over before. This is the kind of mistakes I always make too, James. Don't worry about it. All right, well, anyways, imagine that plus charge is not there. We'll have to fix that later. Remind me to fix that later, James. So then another water molecule comes and deprotonates it. And there we go. Watch that swizzle jiggle. And here's the reaction coordinate diagram. First step is rate determining and endothermic because we only break a bond. Next step's exo and the final step's exo as well. As you can see our humps. This one's got 3 steps, huh? And you could tell the rate determining step's got the greatest activation energy. Second step's lower activation energy, and the third step's low activation energy. So the first step is definitely endothermic because all that happens is a bond breaking. It takes energy to break bonds. This second step is definitely exothermic because all that happens is a bond forming. When the oxygen of the water adds to that carbocation, it makes a bond, releases energy. And the last one, this is actually a little bit stronger acid than the hydronium. I think this pK is probably like minus 2.2 or something. This is minus 1.7. So, yep. And then we got transition states even. Look at that. It's looking more like products. So the bromide is mostly negative and the carbon is mostly positive. And the second transition state's looking like reactants. So this water molecule is kind of far away. Carbocation is still pretty positive and the water is just starting to get positive. Transition state 3, we got the delta positive on the oxygen here. It's still a lot, plus 3/4 very positive because it's only looking like reactants. And that's only a fourth because it's looking like reactants. There we go. Watch that swizzle jizzle. It's now trending on Twitter. Dope. I'm done. I quit. All right. So James, remind me, we got a bunch of pluses to fix here. Plus. That's easy though. We'll get to it. Good work, James. Okay. So now, and let's get back to what we were doing. Oh, you know what I'm going to do? I'll start the lecture off with one of the problems like I just added to homework 5. Remember, I just added, which one was it? It was the, not that one. That one, I like these ones. Okay, let me make up something like this. These are cool. See if you like it. Oh no, darn it. I told myself not to do that. I was charging my Apple Pencil and I don't want to bend it. I feel like I'll break it. I shouldn't charge my pencil that way. I should use a cord. Probably safer. Oh, Mary, is Mary here? I don't know if she's here. If you're here, Mary, charge your pencil. Okay. Oh wait, you don't have lab today though. Never mind. Okay, let me make up a new one of these. I'll make a cyclic one up. So let's say we have some molecule like, some molecule, I'll make it a 5-membered ring. And I've got this guy. Yeah, this will work good. I got a wedged out sulfur there. And then I don't know the stereochemistry of this guy or the identity. I don't know my nucleophile. I'll say my solvent is like acetone. And my product is, I'm giving away too much. We're going to leave that blank and we're going to say it's achiral. 0 degrees rotation. Okay, so what is, oh, I have to do one other thing. I also have to do, let's go like potassium and chloride. Okay, so this is a nice little puzzle. Let's work it out together. Let's see if you can help me. So I need to figure out what this X is and what this is to give me an achiral product. What do you think X is? What's the identity of X? If you're looking at what I got, all the information given. Okay, I'm seeing a lot of chlorides. Yeah, I agree. It looks like X is the chloride because that's the leaving group, right? That came off. So it left as a chloride. That makes sense. And then good. And now what about the product here? It's achiral. What kind of things do we know are achiral? What does that make you guess? Something that's a achiral member of a set of chiral, achiral member of a set of stereoisomers, at least one of which is one or more of which is chiral. So an achiral member of a set of stereoisomers, one of which is achiral. Hint, soup. Yes, meso compounds are achiral, aren't they? Meso, that's what you should be guessing, right? So wait, how could this be turned into something meso? What would it have to have? What do meso compounds have about them that makes them easy to identify? They have symmetry. They have an internal plane of symmetry, right? So I need to have like a plane of symmetry about this type of molecule, but in the product side. So like maybe down the middle here. So what should on the product side, what should this be if I have an internal plane of symmetry? What do I need to put here? And I want it to have an internal plane of symmetry, so it's meso and achiral, right? So I'm seeing a bunch of thiol answers. Okay, so I like that. Is this, I'm going to put a thiol and SH here. I'm going to put SH here. Should it be dashed or wedged? It needs to be wedged if it's going to be chiral. Does that make sense? It's meso. Okay, cool. So if I'm going to have this SH on here, wedged like that, what kind of nucleophile did I have then? I need a nucleophile here that's going to kick off the chlorine. Going to need a thiol, right? I'll make it red. I don't know why I didn't make the other one red. SH minus, right? And what kind of spectator ion or groupie am I going to have here? It's going to be the potassium, right? Because that's what it showed up in the product side. Awesome. And now I'm going to draw this fully, this one. I'm going to include my thiol that started on here. And then I need to draw the chlorine here. But is this chlorine that I have to draw here, the leaving group, is it the wedged or dashed? Ryan's guessing dashed. So Annalise, I like it. Yeah, it's got to be dashed, right? Because then when my sulfide comes in and kicks it off, it's going to invert. So it's going to be wedged as a product. Nice. Do you like it? I like it. Combining SN2 and Stereochem. You can tell I like to combine material from all the chapters together. It's nice. I don't just like lose the the Stereochem stuff when I start chapter 6, keep it going. Okay, good job. So now when you look at our example in the lecture outline, hopefully it's obvious now. It's becoming more obvious, like, oh wait, I got a cyanide, I got a nitrile here. So X has got to be, what do I need here? What do I need here? The electrophiles there. Yeah, you can see it, I'm thinking. I won't give it away. You can ask me if you have to take a guess at it. All right, so back to chapter 6. We did some SN2. Let me do this. I'm going to review really quick the Well, I'll show you something I added to the. I added the Heather Fletcher sheet from before. So this one, I showed this just this picture she drew, the inversion and then the overall reaction, but here she has the mechanism in there. And then so S is for substitution, N is for nucleophile. I like to say nucleophilic here. And then biomolecular rate determining step, electrophiles inverted. There we go. Details. She shows the blah, blah, blah. Oh, and this I'll talk more about it later. Usually if you're stereo center if you have a stereo center on the carbon with the leaving group, if it's R, it normally will become S, but not always. It depends on your nucleophile and your electrophile. But there always is an inversion of configuration, we say, but it doesn't necessarily go from R to S or S to R. Okay. Another thing I was going to show you, I was going to click through this really quick. So the key to understanding this chapter and just like everything from now on is to have the mechanisms memorized in your head to where you don't even have to write it out. You can see the whole thing. Look up on the ceiling like Queen's Gambit, and you see it all playing out, right? Those of you, I think most all of you had the radical halogenation mechanism down like that. You can do it all in your head before exam 2, and you did really well on exam 2. Those of you who didn't have the mechanism in your head that well, so you can just see it, yeah, that really hurt you on exam 2. So I want us all to do better on exam 3. Even those who did good on exam 2, I want you to do better on 3. So memorize, practice drawing these mechanisms out over and over, get good at them. So let me show you what I mean. So this is the quiz you'll have on Monday, Tuesday next week. You'll fill in these boxes. S is for substitution, N's nucleophilic, biomolecular. And then here's an overall reaction example. Got our solvent and everything. So the key is the mechanism. You should be able to see this in your head. That sulfide's coming in, backside attack and inverting the deuterium, that carbon center, right? There we go. And then number your carbons. That's the key. So easy to lose carbons without numbering it. And then we did this last time. So this is a concept I have. This will kind of get into my rankings here. So you know what? I'll pause on this. We'll get back to that next time. Let's go into chapter 6 lineups. So now for this, we're going to look into the nucleophiles, the electrophiles, solvent, and we'll consider the stereochem, which we've already discussed a lot of this, but I'll just kind of more formally talk about it all. I think it's better to do it on the Jamboard. Those old PowerPoint slides kind of put me to sleep. I think I'm just going to go periodic trend on this guy. So in terms of the nucleophiles, what? Lost my cursor. So nucleophiles. So negatively charged versus neutral. What do you think makes a stronger nucleophile? Nucleophile with a negative charge or the nucleophile with no charge? So let's look at, for example, water versus hydroxide. What's the stronger nucleophile, would you guess? Yeah. Having negative charge makes you much stronger. MuCH. Yep, much stronger. And much stronger. And when I say much stronger, I mean makes the SN2 reaction faster. So SN2 reactions, when we're ranking things, all the SN2 rankings are based on speed of reaction. Because the SN2 reactions under what we call kinetic control. Does anybody remember what that means if you're under kinetic control? If you're under kinetic control, kinetics refer to the rate of the reaction. If your reaction's under kinetic control, that means product formed fastest is the major product. So that's why we look at the rate of reactions for SN2 reactions. Other reactions, we won't look at the rate. We'll look at the energy of the final product, and whatever final product's lower in energy is the most formed, but not for SN2. So yeah, let's look at another one. Let's go. Nucleophiles. Okay, who's faster? That hydroxide again versus acetate. Who do you think's the stronger nucleophile? I'll tell you more about these. The acetate has resonance. It's got a lone pair of electrons, a single bond, and a double bond. So it's definitely got resonance. And you could draw the resonance hybrid, of course. Are either of these resonance structures the major one or the equivalent? They're the same. So each oxygen gets -1/2. Okay, so I said more negative charge, faster reacting nucleophile. So this oxygen has a full -1 charge. These two oxygens only have half a negative charge, and only one of them is going to react with the electrophile. So who reacts faster? That one's stronger, faster reacting. Nucleophile. Yeah, full negative charge versus half a charge. Okay. Let me glance at my notes here. I don't like that basicity stuff. Yeah, I'm not going to do that. You're all lucky. I've gotten better at explaining this stuff. Okay. Next up, so that was negative charge. Having negative charge makes you a stronger nucleophile. The next thing I'll talk about is periodic trends. Ooh. Turns out, if you're looking at the periodic table, and you've got like hydrogen over here, you got these transition metals, then you got the best metal, the best elements over here, the NMR, the organic chem ones, you know, like boron, carbon, nitrogen, fluorine. Did I miss one? I did. Skipped oxygen. Oxygen, fluorine. All right, you got those ones right. It turns out nucleophiles get stronger this way. And they get stronger down. So increases to the left and increases down. So does this trend, the nucleophile trend, does it follow along with any other trend we've learned? Does that work for like acids and bases? Or bases, say base strength. Do you get stronger as a base going to the left? You do get stronger as a base that way. But do you get stronger as a base down? No, you get stronger as a base up. So it doesn't really follow the base trend exactly. What about electronegativity? How does it relate to electronegativity? It's opposite. Right? Completely opposite. Electronegativity increases up towards fluorine and then to the right towards fluorine, right? So nucleophilicity, we can say, yeah, I'm saying nucleophile strength or nucleophilicity. That's a big fancy word. Let me write it for you. C-I-T-Y, nucleophilicity. I spelled that pretty bad. Let me try to type it. Nucleophilicity, the nucleophile strength. Nucleophilicity. So nucleophilicity increases down and to the left. So opposite of electronegativity. Does that kind of make any sense to you? Say, for example, if I'm thinking of a nucleophile, just a generic nucleophile, it's going to react with an electrophile, some electrophile. It's got a leaving group here. It's going to react by reaching out its electrons, right? Leaving group will leave. Does it make sense that this nucleophile, if it's not that electronegative, it's easier to reach out its electrons and react? Should make sense to you. If I'm a very electronegative atom, I hold my electrons tight. I don't want to reach out to an electrophile. I want to hold them tight. If I'm not so electronegative, then my electrons are loosely held and they can reach out and attack electrophiles easier. Okay. And let's look real quick at our periodic trends. I got this here, animations. Yeah, let's do this. O.Chem periodic trends. Let's copy this. I'll put it in this week's stuff again. All right, so we got a periodic table. In terms of size, who remembers what happens to the left? Do you get smaller or bigger as you go to the left? Your size increases to the left, but only increases a little bit. See, I used a really skinny arrow. The reason why you get a little bigger to the left is because the atoms are less electronegative. They're not holding their electrons as much. They're less electronegative to the left. And then down, it increases a lot, because you're adding on lots more electrons as you go down the periodic table. So when you go from fluorine to chlorine, you're adding on all kinds of extra electrons and just keep getting bigger and bigger. All right, and now electronegativity, we know this one, it increases towards fluorine up and down, up to the right and to the up, right? Base strength, you go stronger to the left and weaker down. It's stronger up like that. And now nucleophile strength, it's our new one. So it's going to get stronger this way. So it's the opposite of the green electronegativity, because it can reach its electrons out. And you get stronger down. And then the nucleophile strengths down, they can change depending on your solvents, but let's just go with them. Those are kind of exceptions. Let's just say our rule of thumb will be get stronger down. And then there's something called polarizability. So I hadn't talked about this before, but now we can. This is part of this chapter. Polarizability, it's a description of how loosely electrons are held. So if I'm an atom that has, usually I'm a nucleophile and I'm the atom with the negative charge, it's going to reach out and attack an electrophile. Polarizability talks about how loosely my lone pair of electrons is held. If my lone pairs of electrons are held very loosely, then I can reach them out easily and attack an electrophile. But if they're held tightly, I squeeze them in. So an atom that has loosely held outer electrons, like the lone pair that's reacting, they're said to be more polarizable. I can polarize those electrons out and grab an electrophile. If I'm not as polarizable, I pull them into me. And I don't react as fast. I'm not as good a nucleophile. So with that idea of polarizability, what do you think the trend is? Do you get more polarizable when you go left on the periodic table or right towards fluorine? More polarizable to the right or more polarizable to the left? You get more polarizable to the left. So it's the opposite of electronegativity. Remember, electronegativity, pulling in electrons. Polarizable is talking about letting them loose. So polarizability is going to be opposite of electronegativity. So what about polarizability for down or up a periodic table? Will polarizability increase down the periodic table or up the periodic table? It will increase down the periodic table. So it's opposite of it's opposite of electronegativity again. Yeah, because the less electronegative you are, the more loosely held your electrons are, the more easily they can reach out and react. Let me see, is there another trend? I don't know why I put the acid stuff out there. I got to reorganize this thing. Every time I look at this, I'm like, oh yeah, I should reorganize this. But I'll just take what I got here. Oh, I didn't snap that very good, did I? I'll pause on the acid-base strengths here, but we don't need to look at that right now. Okay, so atoms that are more polarizable are better nucleophiles. See how polarizability and nucleophilicity are the same? They both get stronger to the left, and they both get stronger down. Okay, let's do some examples off of that. Who is the stronger nucleophile? Remember, the nucleophiles, they want to reach out and react with electrophiles. I want to reach out and react. So who is stronger? The hydroxide or the fluoride? Stronger nucleophile reacts faster, hydroxide. Because it's not as electronegative. So the negative charge, the lone pair of electrons aren't held in as tightly. They're allowed to reach out and attack a electrophile. Okay, let's do another example. What about an amine? Nucleophiles don't always have to have negative charge, right? They can have neutral charge too. So an amine versus the phosphorus analog. Who's the faster reacting nucleophile, would you predict? Reaching out for an electrophile, right? Yes, the amine is, oh, no, not the amine. One of you put amine, and I don't know why. I'm too empathetic. I'll choose your wrong answer. But if I ask you a yes or no question, you answer quickly, you can fool me into agreeing with the wrong answer. I don't know what that is about me. I guess my empathy makes me a good teacher, but not always saying the right thing. Stronger. All right. All right, so stronger because it's more polarizable. See how it's like lower than nitrogen on the periodic table. So its electrons are more loosely held, they can reach out. Let me see, I got the basicity. I think this next one, charge, sterics. Oh, sterics is another good one. Yeah, let's do that. That's not too bad. So we're still ranking nucleophiles here. Let's look at their sterics. Remember, sterics is describing their size. So when a nucleophile goes in and reacts with something, should it be small, do you think, if it has to do that backside attack, squeeze in on that electrophile? Or do you think it should be big? Versus small. So which one's a better nucleophile? Small is better. Small. So imagine, this is where I came up with this concept a few years back. I really like it. Imagine we have electrophile, say a secondary electrophile like this. We've got this bromine here. And we got a CH3 there. We got another CH3 here, and then a hydrogen. So I got a secondary electrophile. And then I've got some nucleophiles that are going to come in, try to react with this. So the nucleophile is going to do the backside attack here, and the leaving group's going to leave. Like that. Okay. So as the nucleophile comes in, if it comes in a little off course, like so, if it's a little off course, it can hit this methyl and then bounce away and not react. That'll slow it down, because in order for the nucleophile to react, it needs to do three things. Nucleophile to react. Change the size of this caption. Red. For the nucleophile to react, it needs to do three things. Can someone tell me what are they? What are the three things? One, it has to what? Collide with the electrophile, right? Two, it has to collide which way? With correct orientation, right? It has to be a backside attack. That's what we believe. It comes in from the front, no reaction. And, oh, what am I doing? Three, it has to collide with enough energy. Or speed, right? So our nucleophile, if it collides like into the bromine, it just bounces off, no reaction. If it hits this methyl, boom, just bounces off, no reaction. If it hits this hydrogen, bounces off, no reaction. If it comes in just backside attack, but really slow, it can still just bounce off because it's not quite enough energy to pop off that bromine. But if it comes in with enough energy, fast enough, and correct orientation backside, boom, it pops off and it reacts. So this concept I was saying that I like is I like to think of the backside attack happening in like a cone of reactivity. I'm going to draw a cone right here. So let's say it has to come into this cone of reactivity. It reminds me, it makes me think of a Get Smart. Anybody see that movie or the old TV show? At the cone of silence. Yes, it's got to be small but mighty. So if your cone of reactivity, if you're a big nucleophile, if you're a big guy, it's hard to get into that small little cone, right? But if you're small, if you're a little dart, you can get right in. All right, so with that in mind, let's compare some. What do you think's a better nucleophile, a faster reacting, stronger nucleophile? T-butoxide or hydroxide? They're both negatively charged. They're even there. They're both oxygen, same electronegativity, same polarizability. But the T-butoxide is much bigger, right? So this is the smaller, stronger, faster nucleophile. Got it? Let me see, I gotta make up another one. Let's go. Who reacts faster? Smaller, faster. They're both negative charge, which helps make them react fast. They both have sulfur, which is not that electronegative, polarizable. So they're even there, but the size, the smaller one, is stronger. All right. I think I covered all the nucleophile stuff I want to cover. Oh, I want to show you this table. So this table is describing a reaction between iodomethane. So I got the CH3I, and it's a nucleophile with methanol as the solvent to give the, I'll make it. It could be negative or positive. I'll make it negative in this case. And then the iodide came off, right? All right. So does this table then make sense that like methanol is if methanol is both the solvent and the nucleophile, if I just have methanol in there, it has a relative rate of 1. So the methanol can be the solvent and the nucleophile. And when that's the case, you get a rate of 1. All right, well, if I add into this methanol some nitrate, and nitrate looks like so, NO3 minus, right? Yeah, there we go. There's nitrate, and it has resonance. That'd be good practice for you. Practice do-yo this resonance, do-yo. Do-yo. Do on your own, try to draw those resonance. And then the hybrid will look like this. And each of them are sharing a -2. So it's going to be -2/3, -1/3, -2/3 for every oxygen, -2/3, -2/3, -2/3. There we go. That adds up to -2. Good. All right. So why is this nucleophile reacting 32 times faster than the methanol? Why is it reacting faster? Because the methanol only has a delta minus, it's like a fractional minus charge, and it's going to be less than -2/3. So we can say, I mean, we know it's more electronegative than carbon, so we'll have some draw towards it because of that. But it's overall, we'll just say it's got a 0 formal charge, so it's not as negative. So it's slower. Okay, next up, we've got the fluorine. Why would the fluorine be faster than the nitrate? So fluorine, interestingly, it's to the right of the periodic table of oxygen, but so it's more electronegative, which hurts it. But what then must be the reason why it's faster? So this is really science right here. Science is all about making up some stuff, making some guesses, and then testing it experimentally. And when you get your experimental results, make up some more stuff. So you're just BS in the results. So my results are just going to be like, oh, fluorine's faster. Of course. Yeah, that's faster. So that must be because, oh, it has more negative charge. It's -2/3 minus 1. And well, it's more electronegative. That's bad, but it's smaller. Oh yeah, it's smaller. That's it. So you just BS whatever the results tell you. And you use that BS to get your BS in chemistry. And then when you're done with that, you go on to grad school and you get your PhD. You just pile higher and deeper. Just pile that BS higher and deeper, PhD. So, and but I'm making a crude joke, but it's true. Science is just about guessing, making an experiment to test your guess. If the experiment says your guess is wrong, you got to make up some other stuff. Alina says the video is freezing up a little bit on her. Is anybody else having problems? I'm not. On my end, it looks okay. Okay, yeah. Yeah, sorry, Alina. Okay. Oh, Alina, you can keep the Jamboard open if that might be better than the video. All right, so let's look at that fluorine. I'm going to emphasize this. So I'll do it on the next page. So the fluoride, I'm sorry. So I got the nitrate. Oh. Nitrate versus the fluoride. So the oxygen of the nitrate has a -2/3 charge. The fluorine has a -1 charge. That's making it stronger as a nucleophile. The fluorine is more electronegative than oxygen. So that would make it a weaker nucleophile. So let's do this. Stronger nucleophile. Weaker nucleophile. And then the fluorine, is it more or less polarizable than oxygen? Is less polarizable than oxygen. That would make it then a weaker nucleophile. And what about size? Fluorine is what? Smaller or larger? It's smaller. So does that make it a stronger or weaker nucleophile? Oh no, stronger nucleophile, sorry. So we got all kinds of trends bucking each other. We're like, oh, we're stronger. No, we're weaker. We're weaker. No, we're stronger. So in this kind of case, this wouldn't be a question I'd ask you on the exam. I wouldn't say, ooh, of these two, which is stronger? Because there's they like contradict each other. So when we get to this point, we have to go run the experiment in lab and get the results like we do here. It turns out that the fluorine is stronger by lab results, because we saw on the last table the fluorine react 500 times faster than methanol, and nitrate just reacted about 32 times faster. So it looks like the -1 overall charge versus -2/3 and the smaller made a bigger difference. There's many things in science that you don't have a cut and dry answer. You just do the experiment, and that's okay. When I write my exam questions, I'm very careful to make the situation such that you can determine the answer. I don't give you this ambiguous ones. Let's look at some more. Let's compare the nucleophiles bromide versus iodide. Remember, on the periodic table, it goes fluorine, chlorine, bromine, iodide, right? So size increases down. So which is the stronger nucleophile, bromide or iodide, do you think? Yep. Stronger. You can see it down here. It's listed at, it's 26.3 million times stronger than methanol. And bromide's just, a measly 617,000 times stronger than methanol. This trend, as I mentioned earlier, they could switch if you don't have this solvent we're using is methanol. It's a polar protic solvent. I think if it's polar aprotic, the solvent, which I'll define shortly, it might switch, but let's just stick with, I won't give you those exceptions. Okay, so now let's look at like this thiol. Why is this thiol the champion here? What's up with that? I mean thiol, this hydrogen sulfide. Why is hydrogen sulfide so great of a nucleophile? It reacts 100 million times faster than methanol. So what are some properties about it that makes sense? Like, oh yeah, that should be a good nucleophile. What is it about it? It's small, good. That's good. Check. What else? It's got a -1 charge, a full -1 charge. Good. What else? It's polarizable. Not too electronegative, right? So on the periodic table, we have oxygen and sulfur. So it's like below, it's going down on the periodic table, right? Yep. I don't know, is there anything else? Oh, the steric hindrance. Not much. Because it has just a tiny little hydrogen attached to it. So when we talk about steric hindrance, you don't talk about the atom with the negative charge, because the atom with the negative charge, if it's big, it helps. It's more polarizable. Steric hindrance, you refer to the rest of it. So let me make a little side note. I want to make sure. Sometimes students get confused on this. So our nucleophile, we have like the atom with the negative charge, right? And then you have the rest of it. The rest of it is where you consider steric hindrance. Just the rest of it. Because the bigger this atom with the negative charge that's going to react, the better, because it was bigger, it's more polarizable, it can like reach out its electrons. But the rest of this you want small. Okay. Okay, so Annalise, I think I just answered your last question on the chat. You were saying bromine is smaller than iodide. But when we're comparing bromine and iodide, we're just comparing the atom with the negative charge. So it's not really a comparison of steric hindrance. Steric hindrance is to deal with the rest of it. Let me make another example of this. Let me make sure. I wish I had more room. That's okay. I'll make it work. Let's do another. Does yellow work for people? I try to avoid yellow usually, but I'm going to do it. So like if I have the butyl versus hydrogen sulfide, what's the stronger nucleophile? Less steric hindrance, because this is the rest of it has less steric hindrance. All right, and now I'm going to talk about the rest of the SN2 categories. We covered nucleophiles. Now we're going to cover electrophiles. So for electrophiles, it's pretty easy to understand with electrophiles. Nucleophiles are the ones that take the longest time to talk about. With electrophiles, we have methyl, and then say like an iodide or something on there, right? So there's a methyl electrophile. And then we have primary, so it would be something like this. Secondary. And then tertiary would be, I'm gonna draw it down here, something like that. Okay. So for an SN2 reaction, which do you think reacts the fastest? The methyl electrophiles, the primary, the secondary, or the tertiary? And I'll tell you a little more about it. I like to think of these in terms of their cones of reactivity. The methyl has a very large cone of reactivity, because when my nucleophile is going to try to come in, it can come in like here and react. It can come in here and react, here and react. It's got a lot of ways to react. If it does come all the way out here, it bounces off and it doesn't react. If it hits over here, boom, it doesn't react. But it's got a lot of areas. The cone of reactivity is big. All right. And then for my primary, that cone of reactivity is getting smaller because I got this methyl over here. So do you see how my cone of reactivity is not quite as big? So who reacts fastest? So methyl is fastest. Who's next most fast, do you think? Then primary. Then secondary. And tertiary. we say no reaction. It's too crowded. So tertiary is so slow that we'll say it won't even happen. It's just too crowded, too much steric hindrance. And now we're ready to look at my chapter 6 stuff. Oh no, is it in chapter 6? That's chapter 5, isn't it? I need to go to this guy. So this is the one I'm going to email to. Oh, actually, no, I made this up as a Google slide. I have this at the end of here, but yeah, it's not my favorite. Sorry, let's go. It's on the quiz, huh? Yep. What? No, what am I doing? Oh. Learn how to read, Mark. Stereochemistry quiz. That's not the one. I want the SN2 quiz. That's what I want. All right, there we go. So substitution, nucleophilic bimolecular rate determining step. This is a primary electrophile, blah, blah. We got the hydrogen sulfide. That's a great nucleophile. Doing the backside attack there. Okay, a little review, number of carbons, blah, blah, blah. All right, now this is what I'm talking about. I got a methyl electrophile, big cone of reactivity. Do you like it? Is it making sense? Then a nucleophile, even this nucleophile, which has a lot of steric hindrance opposite the oxygen that does the reaction, still thinks, oh, this methyl electrophile, nothing but room. I might miss sometimes and hit the hydrogen, not making the cone, but a lot of times I hit that cone of I get right in that cone of reactivity. And so I collide with that correct orientation in the cone of reactivity. And I collide with enough force to overcome the activation energy, get my product. There we go. And you can see I inverted these hydrogens too. See how this wedged and dashed hydrogen are pointing to the left, and now they're pointing to the right. And the in-plane hydrogen was to the left, now it's to the right. Primary. So primary also has a cone of reactivity, but it's smaller. See the smaller size because of this methyl gets in the way. So this ethyl sulfide, this is an excellent nucleophile. Has a little bit of steric hindrance, not as much as the T-butoxide up here. And still plenty of room. It might hit this hydrogen off the methyl though and miss, but then when it gets in that cone, there it goes, it reacts. Inverts everybody. Good to go. And then it fits in like a glove. Has anybody seen Ace Ventura: Pet Detective with Jim Carrey? I'm thinking you're younger in general, so you would think Ace, you'd know Jim Carrey from, he's not the Scrooge. Who is he? Dr. Seuss's character who hates Christmas. The Grinch. He's the voice of the Grinch, or he actually is in the costume of the Grinch in that one, that's not animated. But he was in a movie, Ace Ventura: Pet Detective. Pretty funny if you want to check it out. So like a glove, it fits in there. And then now, secondary electrophiles. Will it react? Will secondary electrophiles do SN2? Do you remember? They will react, but my cone of reactivity got smaller. Some hindrance there, but I'll make it work. Is cyanide a good nucleophile? Excellent nucleophile. It's got a negative charge. The carbon is not right up next to fluorine. It's got a little bit of polarizability. And the steric hindrance, very little steric hindrance. It's triple bonds holding that nitrogen back, and it's like a dart. So it could still miss. It hits there, but oh, it missed again. It's got two methyls in the way, but it can eventually get in there and do the SN2 reaction. So, yep. And then tertiary. Now, tertiary, its cone of reactivity is tiny, right? Because it's got these three methyls with all the hydrogens in the way. So even this nucleophile, which is pretty good. It's like, no, this is like the Galleria Mall parking lot on Black Friday. No dice. No way I'm going. Nope. Bank. Doink. Bank. Nope. Can't get in there. So no reaction for tertiary. So yeah. So too much steric hindrance. Wait for Cyber Monday sales. Skip the Black Friday sales. Unless you're having fun in the crowds, you can park across the street, walk, get some exercise. And then this one, it's kind of a crude joke. If the glove don't fit, you must acquit. Another old reference. I'm not sure if you know who. How many of you don't know who this person is? I think some people won't know who it is. O.J. Simpson. That was the big scene in his trial to get him off of the murder charges. The glove didn't fit. And so this the nucleophile won't fit. All right, here we go. So you're gonna have a mechanism quiz for that material you just saw on Monday, Tuesday. Here it is. It's gonna be those same things. You're gonna fill in all these boxes like you saw, and you're gonna fill in what happens here, the products, and if there is no reaction, you'll write no reaction, just like we went through. Okay, let's see. So we finished electrophiles. Now leaving groups are even easier. Let me just make sure I covered what I want to cover on these. Look at those later. Oh, this one's kind of interesting. Does this one make sense? The branching. Yeah, I'll do one more thing with the electrophiles. One more thing for electrophiles. So if I compare, say, this one to this one, what do you think? Who's the better electrophile? Someone said the primary. This is a primary electrophile, and this is a primary electrophile. So you were correct. The primary electrophile is faster. But this one's got a bunch of branching. So when I try to draw in the rest of this, you can see that like my cone of reactivity is going to be smaller for this one than it will be for this one. Could be a little bigger because it's got less branching there. Stronger electrophile. And oh, I had some data on it, huh? So you can see how when this comes up, come on, Jambo. So this one, this is just a primary electrophile with no branching. This is a primary electrophile with one methyl branch. And then this is a 2 branches, primary still. So these are all primary, but the branching changes the rate. Hopefully that's making sense. With no branching, less steric hindrance, reacts fastest, and then these guys react slower relative. So Ryan's asking, is this a tert butyl? Yeah, we can call that a tert butyl. That's right. 4 carbons like that. We can call it tert butyl. Oh, I want to do electrophile, but we're going a long time. Let me just do it really quick. Then we'll do solvent next time. Yeah. not electrophile, I'm sorry, leaving group. This will just be really quick. The leaving group is just, it's an easy trend. To rank the leaving groups. All you do, have the leaving group leave, then rank it, its strength as a base. So we've done that before. We've ranked bases, right? And then we predicted their acid strengths based off them. So this is not new to us. So for instance, if I'm going to compare like fluoride as a leaving group to chloride, or I'll make it even better, bromide. What's the better leaving group? So if I have them leave, I have some nucleophile attack them. And I compare the two leaving groups after they've left. And if I know which one's the strong, the weaker base, that's going to be the stronger leaving group. So which one of these two is the weaker base? Bromide's less less basic, yeah. Bromide is the weaker base. It's so if it's a weaker base, it's more stable. Oh my goodness, what I do? It's more stable and the better leaving group. The more stable is the way I like to think of it. If it's more stable, what that tells me is that when it comes off, it's like happy to be off. And so it's a low energy thing. And so these are usually, yeah, they're exothermic. So the transition state, I don't know if that helps that much, but I don't know. That's the trend. So iodide is one of the best leaving groups. It's a very weak base. Its conjugate acid is extremely strong. And then bromide's a good leaving group. Its conjugate acid is really strong. It's a weak base. And as you go down, you can see these leaving groups become worse as you pull them off. For SN2. So last thing we'll do for SN2 is solvents. We'll do that next lecture. That'll finish off chapter 6. And then we'll start chapter 7 on Monday. And chapter 7, I'm still thinking I want to do the mechanisms for the exam, but I'll show it to you and I'll talk more about it on Wednesdays, because I think it'll be good for you for that exam. It'll be nice. Maybe you might like it to have, you know, for sure you're going to just have these mechanisms on exam 3. So it's like some points that should be obvious.